Okay, fantastic. So I have the pleasure of talking to you this morning about secondary eclipses and phase curves. But before we get started, I want to interrupt our regularly scheduled programming with a brief advertisement for the Apex department. This is a new department at the Max Planck Institute for Astronomy in Heidelberg, Germany, and it's focused on all things exoplanet atmosphere characterization. So observations, theory, instrumentation, we've got all of it. And most relevantly for you guys, we are hiring. With a small caveat, we're not hiring this very second, but we will be. so please don't mob me after the talk. But keep an eye on the AAS job register. We're hiring at all levels, so grad student, postdoc, and staff. And if you're interested in learning more about what we do, feel free to come talk to me. Okay. So what is a secondary eclipse? You guys know this. This is when the planet goes behind the star, and any thermal emission or reflected light from the planet is blocked. And so by comparing the baseline where you have the planet plus the star with the secondary eclipse, when you have the star alone, you can tease out the thermal emission and reflected light signal from the planet. A little bit of history. So the very first detections of thermal emission from an exoplanet came from the Spitzer Space Telescope. I want to give a little shout out to Spitzer since the Spitzer Science Center was here on Caltech campus. Spitzer was like the little telescope that could. It was really a pioneer in the detection of thermal emission going all the way back to 2005, so almost 20 years ago. And here are two eclipse observations of different hot Jupiters. And in the next 20 minutes, I'm going to take you on a whirlwind tour of all the science that happened after this. Okay, so just to give everyone a feeling of the type of signal we're looking for, this is our favorite Planck functions for black bodies at different temperatures. You all know that the luminosity is proportional to the temperature to the 4th power. I remember learning that in physics as a student, and I was like, okay, cool, temperature to the 4, that's great. But when you really want to detect this, that power to the 4th is super important. That's a big number. So the cooler you get, the harder it is to detect the thermal emission. And in addition, the colder planets have black body curves that peak at longer wavelengths. And so if you really are interested in thermal emission, you want a big telescope that operates in the infrared. So I already mentioned Spitzer is a key facility for detections of secondary eclipses and phase curves. Hubble Space Telescope has also been a really big player, particularly for spectroscopic measurements of eclipses and phase curves. And of course, all of you guys know JWST. Here's a rough schematic showing the sensitivity of these different facilities to different types of thermal emission spectra. So I'm showing here the predicted planet-to-star flux ratio versus wavelength for two typical cases. So one of them is a typical hot Jupiter with a temperature of about 1500 Kelvin, orbiting a sun-like star. That's shown with the dashed line. And the solid line is a warm rocky planet. So this is about 400 Kelvin orbiting an M dwarf. And then I color-coded on this figure the sensitivity of these 3 different facilities to thermal emission measurements. So you can tell that Hubble was fairly limited in what it could see simply because the wavelength range was too blue. There's Spitzer IRAC. So Spitzer IRAC was a workhorse for hot Jupiters. And now with JWST, we can, for the first time, really start pushing down to smaller planets and cooler planets, which is super exciting. Okay, so planets are not actually black bodies. They have spectral features, which is really exciting because we can use that to learn about their chemistry. And to illustrate how this works, I have a couple of cartoon schematics. On the top left, you're seeing the opacity of the atmosphere as a function of wavelength. So here we've got a typical think of this not as a single spectral line, but a spectral band. This is the temperature pressure profile of the atmosphere, so how the temperature changes with height. And then on the bottom left, I'm showing what the thermal emission spectrum of the planet could look like. And so in this case, because the temperature is constant with altitude, the planet just looks like a black body. So even though in this absorption region here, you'd be probing a higher layer in the planet's atmosphere, the temperature there is the same, and so the planet looks like a black body. If instead your temperature is decreasing with altitude like this, you get an absorption feature down here. So at the wavelengths where you're more opaque, you're probing less deep in the atmosphere, the temperature is there is cooler, and so the planet is a little bit fainter. On the other hand, if you have what's called a thermal inversion, so the temperature is increasing with altitude like this, that same spectral feature is going to appear as a bump. So this is a feature in emission rather than absorption, because that higher altitude that you're probing is actually hotter. All right, and then this is bringing us back to our isothermal profile, where no matter what altitude you're probing in the atmosphere, the planet appears like a black body. And so I emphasize this just because it's a little confusing sometimes to interpret these thermal emission spectra, because it depends both on the temperature structure and the opacity of the atmosphere. Is that making sense? Yeah, all right. Okay, lots more examples. Let's skip through these. Okay, so another way you can observe thermal emission from exoplanets is through phase curves. And so the idea here is that if your orbital period is short enough, you can observe a complete orbital revolution of the planet around its star. This is typically, oh no. Okay, this is typically only possible for planets with relatively short orbital periods, so less than a couple of days. And in this cartoon, what you're seeing is the sum total flux from the planet plus the star. So now you've got the hot day side of the planet rotating into view. Here's the secondary eclipse where the planet is completely blocked, and then the day side rotates back out of view. And so phase curves are really powerful observations, because the changing viewing angle reveals different parts of the planet over time. So you can map out the climate and the chemical composition of the atmosphere as a function of longitude. I won't say much about this because Emily Rauscher is going to talk about it on Thursday, but a new frontier that's really exciting is called eclipse mapping. And an eclipse map is measured when the planet is eclipsed by the star. So one slice at a time goes behind the star. And you can actually use this to measure the brightness distribution on the day side of the planet. So stay tuned for more about that from Emily. Okay, so that's an overview of the techniques that we use. I'm going to move on now to talk about what science questions we can answer with eclipse and phase curve observations. So one of the big ones is about climate. So these planets are extremely close to their host stars. They're really highly irradiated on one side and not the other. How is the heat redistributed in their atmospheres? So how do their atmospheres respond to this extreme heating on the day side? What is their temperature structure like? So how does the temperature change with altitude in the atmosphere, and how does it change with longitude as well? What is the chemical composition of the planet, and how does that change with location in the atmosphere? And also what clouds are forming and where are they? What is the overall metallicity and chemical composition of the atmosphere? And finally, for rocky planets, you can use these types of observations to answer the question, do they have an atmosphere at all? And so I'll just walk through a couple of highlights and I know in, what time is it? 15 minutes, I won't be able to get through all of these, but we'll see how far we can get. So this is a very famous phase curve observation. This is the very first phase curve ever measured. It's for a hot Jupiter called HD 189733b. This was back in 2007, work from Heather Knudsen. And just like the cartoon, you can see here the increase in flux as the day side of the planet rotates into view. Remarkably, though, the peak brightness actually occurs here rather than right at the center of the eclipse. And that suggests that there's actually winds in the atmosphere that are circulating heat eastward. This is something that was predicted by 3D models before it was observed. So we get a win for the modelers on this one. After that, there were many more phase curves observed with Spitzer. And this is a nice paper from Tad Kamasek showing the day-night temperature contrast for these planets. So if you measure the day side brightness temperature and you compare it to the night side temperature, that gives you a rough proxy for how much heat is being circulated from the day side to the night side. And you can see this increasing trend here. So the hotter the planet is, the higher the equilibrium temperature is, the greater the temperature contrast is between the day side and the night side. And this is because the hotter your atmosphere is, the less efficient it is at recirculating heat to the night side. Here's another more statistical result. This is some beautiful recent work from Drake Deming. And Drake is a really special guy. He decided after retiring that he wanted to analyze every single Spitzer eclipse observation that ever occurred. That's almost 500. So I think that's what Drake does for fun. So this is the result. So this is the emergent flux of the planet on the day side, normalized to a model prediction that allows you to put all these on the same axis. And what he found is that there's actually a sharp increase in the day side brightness temperature at around 1700 Kelvin. It's still not clear exactly what's causing this. So one possibility is that you could have clouds on the day side that are rapidly dissipating right at that temperature. Or alternatively, you could have the onset of magnetic drag, which is going to slow down the redistribution of heat from the day side to the night side and heat up the day side. So this is this figure to me is really inspiring, showing the whole legacy of what we were able to accomplish with Spitzer. And what I would really like to see is a similar plot to this with JWST 10 years from now. Okay. So here are some exciting results on temperature structure. This is nice work from Tom Michael Evans, where he observed a phase curve of an ultra hot Jupiter and measured the temperature profile on the day side and the night side. And here on the left, you can see the day side emission spectrum. This corresponds to a feature from water. And you can see that this feature is in emission. So the planet is hotter here in the water absorption band. And by contrast, on the night side, you see a more typical water absorption feature. So the planet is cooler in the water bands. And so this is the first evidence we've really seen for a change in the temperature structure between the day side and the night side. And that makes sense because the day side is being blasted with stellar irradiation on the top that's heating up the upper layers, whereas the night side is not. So looking at taking a more statistical view on the same question, this is some nice work from Megan Mansfield, where she looked at all of the thermal emission spectrum measured by Hubble for hot Jupiters to look for trends. And the prediction from 1D self-consistent theoretical models is that the hotter the planet is, the stronger the temperature inversion becomes. So there's one regime here below about, I don't know, 1700 Kelvin equilibrium temperature, where the temperature decreases with altitude. There's a transition region in the middle where the atmosphere is almost completely isothermal. And then the hotter you get, the stronger your thermal inversion becomes. And if you translate these models into some tracks that compare the dayside temperature to the strength of the water feature and also the direction, so whether it's in emission or absorption, you can see that the model predictions fit the data pretty well. So this gray band is showing a range of models that marginalize over a couple of different atmospheric compositions, different metallicities. And so you can see that the trend overall is we reproduce pretty well, but there's also a hint here that there's a diversity of atmospheric compositions because it's not a single line, but rather a spread. So what about clouds? You heard already from Hannah that clouds should be expected and not feared. I totally agree with this. We can learn a ton about atmospheric and physics and chemistry from clouds. And here's another nice result from Spitzer showing the brightness temperature of the day side versus the equilibrium temperature of the planet. And you can see that the day side is increasing in temperature as the planet becomes more irradiated, but the night side down here in blue is actually about the same temperature no matter what the level of irradiation the planet has. And one of the possible interpretations here is that these planets all have clouds forming on the night side, and you're observing the photosphere above the cloud deck, which is at a cool temperature that's approximately the same for all of these. Yeah, I couldn't talk about WASP-43b today because it's currently under review. But if you're interested in night side cloud formation, you can come ask me after the talk, and I'll show you some preliminary results. A little bit more about clouds. So I'm really not spending much time talking about reflected light, but we can also learn a lot about the planets from reflected light eclipses and phase curves. And here's a really nice result from the Kepler mission for a hot Jupiter, Kepler 7b. This is work from Renu, where these different color phase curves are corresponding to different contributions of light. So reflected light and also thermal emission. And you can see that you get a very nice fit to this Kepler light curve with an asymmetric reflected light component. And this could be due to reflective clouds westward of the substellar point on the planet. And this has been observed for a couple other systems as well. So for the most part, hot Jupiters are so hot that it's hard to have clouds on the day side, or at least not high up, but it appears that at least some of them do. All right, so this is an extremely rich topic, and I only have a couple of slides about it, but what can you learn about the chemical composition of exoplanets from their thermal emission spectra? And here are two early JWST results for thermal emission from two different hot planets, a hot Saturn on the left and a hot Jupiter on the right. And you can see qualitatively that these spectra have completely different shapes. So this planet on the left has a strong absorption feature from CO2. That's a hallmark of a high metallicity atmosphere. It's hard to form CO2 unless you have a lot of carbon and oxygen floating around. And so it's really sensitive marker of the atmospheric metallicity. On the other side, WASP-77 has, I'm not going to say no CO2, but certainly much less CO2 than HD 149026b. And so this is, I think, a preview of a vast diversity of atmospheres that we should expect. This is just barely scratching the surface of cycle 1 observations. And yeah, I'm excited to see, is this one typical? Is this one typical? How much does the atmospheric metallicity depend on the mass of the planet? Looking for these demographic trends, and JWC has really opened this up. All right, this result is one for the textbook. So this is the thermal phase curve of the most infamous sub-Neptune, GJ1214b. I'm responsible for the very flat transmission spectrum of this planet. This is like this has been called the most famous flat line in astronomy, also the most expensive flat line in astronomy. Don't shoot the messenger, it's not my fault. But finally, and that was almost a decade ago. So this is one of the results I was most excited to see from cycle 1. This is the this is the broadband MIRI phase curve of GJ1214b. And you can see it, there it is. So this is the first time we've actually like detected anything for this planet. And so what does it mean? And I think that this is, this is still early days. There's a lot of work to do on this data set, but here is a first look. So the data, the estimated phase curve is shown in this black line with the gray error bar. Compared to a couple of different GCMs, these are from Maria Steinruck, and you can see already here that a solar composition model, so 1 times solar, is really good at redistributing heat from the day side to the night side. That doesn't match the data at all. Instead, the models that fit the best are very enhanced in metals, so something like 300 to even 3,000 times solar. And the models are not a perfect fit to the data, but the more metals you put in, the better your fit becomes. And so that points towards GJ1214b being even more enriched in water than the ice giants of the solar system. So pointing towards more of a water world like atmospheric composition than even than a Neptune. Okay. So I'll wrap up with my most favorite topic, rocky planets. And thermal emission measurements are extremely powerful for rocky planets because for these planets, we don't even know if they have an atmosphere or not. We really don't. And as a first test, one of the things that you can search for is evidence for recirculation of heat from the day side to the night side. And so I'm showing here 2 toy models for TRAPPIST-1c, Venus temperature exoplanet, same size as Venus, same temperature. And if there's 0 heat redistribution from the day side to the night side, you get a curve like that. If you get complete heat redistribution from the day side to the night side, you get this solid black line lower down because the temperature of the day side cools off. And this is finally now measurable thanks to JWST. And here's a summary of the results so far. Actually, here's an old one from Spitzer on the left. Here's TRAPPIST-1. Oh, these are backwards. This is TRAPPIST-1b, and this is TRAPPIST-1c. And in all of these cases, the day side of the planet is extremely hot. So that points towards a bare rock scenario. In particular, you can't have very much CO2. These observations were all taken in the middle of a CO2 absorption band. And so certainly Venus-like atmospheres are strongly disfavored based on these data. These planets are all pretty hot, so I don't think we should give up hope. But it is kind of a, after so many years of wondering, particularly about the TRAPPIST-1 system, what these planets are like, it's a little bit like the wave function is collapsing and all of a sudden we actually have some information. So you'll hear more about this topic from Natasha Batalha on Thursday. Okay, so this is my final slide. We're at the very beginning of what is sure to be a really exciting exploration of thermal emission from a huge variety of planets. I put up this terrible slide. This is a complete list of all of the eclipses and phase curves that are planned for JWST cycle 1 and 2. So 23 phase curves, 90 unique eclipses. It's going to be amazing. So I think there's a lot to look forward to, and I'm happy to take questions.
All right, any questions? Perhaps online? All right, I give people to think about questions, and I can ask one as the chair. So among all of these, which one do you look forward to the most?
Oh my goodness. That's a really hard question. I think, so I can't name a single one in particular, but a general class that I'm the most excited about is really this thermal emission from the hot rocky planets.
Yeah, Laura, this is Chaz. To what extent do you see the systematics becoming the limit, particularly for the small rocky planets? I mean, we've seen you can co-add 3 or 4 instances together. Can we add 30 or 40 or 50, which is what some of the early predictive papers require to get down to particularly the high molecular weight atmospheres?
Yeah, that's a really great question. This is like one of the things that keeps me awake at night. I would say, so I'm sure there's a noise floor, but I don't think we've seen it yet. And I'm particularly optimistic for the thermal emission measurements, because in contrast to transits, you don't have to worry about the inhomogeneity of the host star. I think for transits, the limiting factor is certainly going to be our understanding of what the photosphere of the star actually looks like. That's not an issue for eclipses and phase curves. And so we're really just limited by the instruments. As an example, for TRAPPIST-1c, we got to within 10% of the photon noise. It helps that out of 15 microns, the star is not so bright, so the photon noise is relatively high. But I don't know. I think we should keep going and see where the noise floor is.
Nice job, Laura. And I have a question for both you and Hannah, since you both talked about transmission and eclipse, just for the younger people. Can you comment on the complementarity between transmission and emission spectra, or like what the advantages of one or over the other are?
Yeah,
both for all
that is an
planets?
awesome question. And I'm actually going to punt it to later because we have a whole panel where we're going to talk about that. It's a great question.
Thanks for a great talk. So for the TRAPPIST measurements, you took specifically the CO2 band, and that indicates no atmosphere, right?
Yes.
Is there a point in looking in other bands still?
Yes.
And is there a specific band that you're still very interested in and maybe hopeful that after all, we do have an atmosphere?
Yeah, that's a good question. So we focused specifically on the CO2 band because that's the most information rich place to start. Like for a hot planet, the most likely thing to stick around is probably CO2. And so we're sort of testing the null hypothesis. Like if the planet did have a thick CO2 atmosphere, we would have detected a much cooler day side. If you observe out of the CO2 band, that can give you constraints on the amount of CO2 that is present. If it is a bare rock, that can also help you constrain the type of rock. So if I could choose, we should look at all of the wavelengths for all of the TRAPPIST planets that are possible.
Hi, Trent Thomas, University of Washington. So with the emission measurements of TRAPPIST-1B and C, like really cool, learning a lot of information about them. What do you anticipate are the challenges as you go for the further out planets like D, E, and F with the same type of emission measurements?
Yeah, so we'll talk about this more later, but I'm super pro thermal emission, but it just gets so hard the cooler you go. So looking at planet D or planet E is going to require somewhere in the neighborhood of 50 to 100 hours. And so it just becomes extremely expensive. But I still think we should do it.